In this video, we're going to use the Laplace transform method to solve this differential equation. This is one that you saw on your last test that we solved with the standard method. So let's first look at the Laplace transforms. We're taking the Laplace transforms of derivatives. So in taking the Laplace transform of y double prime, we're going to get s squared y of s minus s y of 0 minus y prime at 0. So s squared y of s minus s times y of 0, which is 3, minus y prime of 0, which is minus 12. Then we're going to use this for the Laplace transform of y prime, s y of s minus y of 0. So plus 2 times s y of s minus y of 0, and then the Laplace transform of y is just y of s, so that's minus 8 y of s, and the Laplace transform of 0 is 0. Now we're going to collect everything that is multiplied by y of s, so this s squared, 2s, and minus 8, so s squared plus 2s minus 8 times y of s. No coincidence that this expression here is the same as the left-hand side of the characteristic equation. That will always be the case. And then the other expressions that we have on the left side are minus 3s, and we have a plus 12, and here we have 2 times minus 3, so that's a minus 6, so that's a plus 12 minus 6, which is plus 6 equals 0. Now our objective is to solve this for y of s, which is relatively easy to do in this case. So we just add 3s minus 6, or add 3s and subtract 6, and then divide by s squared plus 2s minus 8. So y of s equals 3s minus 6, and when we're dividing by s squared plus 2s s squared plus 2s minus 8, we are going to factor that just like we did in the alternate method, in the characteristic equation method, s plus 2s or s plus 4, s minus 2. So we're going to divide that by s plus 4 and s minus 2. Now, in order to be able to solve this differential equation, we have to write this right-hand side as fractions for which we know the inverse transform, so we use the partial fraction method. This will have a denominator of s plus 4, this will have a denominator of s plus 2, this is an unknown numerator here of a, and this is an unknown numerator here of b. And we're going to solve for a of b by multiplying both sides through by s plus 4 times s minus 2. So when we do that, on the left-hand side we get 3s minus 6, and on the right-hand side, when we multiply by s plus 4 times s minus 2 times this expression here, the s plus 4 cancels out, and we're left with a times s minus 2. Then when we multiply the s plus 4 times s minus 2 times this expression, the s minus 2 cancels out, and we're left with b times s plus 4. So to solve one of these equations, remember we zero out one of these, all factors but one on the right side, by choosing values of s. So if we choose s equals 2, then the left-hand side is 3 times 2 minus 6, 3 times 2 minus 6 equals, and then 0 plus b times 6, so b equals 0, because, well, let's put another step in there. The left-hand side is 0 equals 6b, so b equals 0. And then we would choose s equals minus 4, and when we choose s equals minus 4, the left side is 3 times 4 minus 6. The right side is a times 4 minus 2 plus 0. That is 6 equals 2a, or a equals 3. And so going back to this expression here, so b equals b equals 0 and a equals 3, and so we are only, so all we have is this, that y of s equals 3 over s plus 4. So let's go back to our chart of Laplace transforms, and we see that we have a Laplace transform of this type on the right-hand side, 1 over s minus a, with the a being equal to 4, so that means we were taking the Laplace transform of e to the 4t, so that is so what we have here in having this as our y of s is that it is 3 over s minus minus 4, which means if we go backwards it equals 3 e to the 4t, and 3 e to the 4t is then our solution of the differential equation. Or let's go over that once more. So remember what we did here is we rewrote this as 3 over s minus minus 4, and we know that the Laplace transform of e to the at is 1 over s minus a. So here our a equals minus 4, so the inverse transform of this, what we call it going backwards, y of t equals 3, this constant in the numerator, times e to the at, e to the minus 4t, and that is our solution to the differential equation. So in this case anyway, the Laplace transform method is very quick and easy, and it gets our constants very rapidly. So once you get pretty quick at the Laplace transform method, it's better than the method we learned before, because you don't have to go through as much of a struggle in getting the constants C1 and C2. So this concludes this basic video on solving differential equations using the Laplace transform method. We'll do a more complex one in the next video.